Hello guys. This is Group 11 final project, and our final project is based on photoelectric effect. My name is Tin, and I'm majoring in business.
Hi, my name is Lin Ong, and I'm majoring in communication studies.
Hi, my name is Lin Bent, and I'm majoring in art.
My name is Sean, and I'm majoring in music. The photoelectric effect causes electrons to be emitted from a metal surface when hit by photons. Our question was how we could use LEDs to demonstrate this effect. And the physics concepts we cover is the nature of light, propagation of light, refraction, heat transfer, and the photoelectric effect. And for the sustainability aspects, we focused on energy efficiency, long-term implications, resource conservation, and renewable energy production. And also, our hypothesis we made for this project is that the efficiency of electricity transferred has a direct and proportional relationship with the wavelength of light that falls on an object. And the prediction we made is that if we shine a light on the LEDs, there will be a current passing through the receiver LED, which acts as the photodiode. And a certain wavelength of the LED will respond to a certain wavelength of the photodiode. So they have to be similar.
So this is the whole procedure of our experiment. And these are the materials that is listed that we're using for this experiment. And this is the whole detailed procedure of this experiment. For the first phase of our experiment, we constructed an LED blinking circuit and employ a voltage to current converter while utilizing an operational amplifier. Next, we integrated a secondary LED into the setup, which serves as a probe for measuring voltages via using a multimeter. However, the initial procedure of this experiment only showed minimal changes in the currents between different wavelengths.
So we want to have enough current to convert into voltage that we will be able to detect, so that our multimeter can pick it up at like higher graph qualities. So what we constructed here is a basic electronic circuit design. It's a very simple circuit design. As you can see, the PD is basically photodiodes, but in our case, we're using a red small LED that it was in procedure design earlier. And then this LED was hooked up in reverse bias. What reverse bias mean is that LEDs usually hook up on positive and negative, and you swap it, as it's called photovoltaic mode. It will be acted as it will convert the photon that receive and convert it into a current. Keep in mind that this will only be same wavelength or lower wavelength. In our case, our red LED is 650 nanometers. So we will be only to be able to detect less than 650 nanometers. And this triangle thing is called operational amplifier. And this resistor, this R and C is basically resistor and capacitor. The resistor acts as basically like the amount of voltage that we want, and we have to set it up. We set it up to about 5 mega ohms, so it draws around 3 volts. And the capacitor is just for frequencies. It doesn't really need to be. And then the TI is the name of the circuit. It's called trans impedance amplifier. You can look it up on internet if you want to know about it more.
This is the whole video of our experiment, and this graph represents the values that we get from the multimeter. From looking at the voltage produced by each of the different sender LEDs, we can observe that there's a decrease in output as the wavelength decreases. This result shows that there's a direct and proportional relationship between the efficiency of electricity, and this properly demonstrates the photoelectric effect. For analyzing the data, we first sorted all the recorded voltage from the multimeter from largest to smallest. Then we made 4 different data points, red, yellow, green, and blue, and we made a histogram plot of it. Following that, we created a trend line and its equation showing the linear correlation.
This is the video of the experiment that we're currently showing you. It's yellow LED, and the voltage is around 140 millivolts, which is around the yellow here 0.1740. That's about 174 millivolt. And we're now doing the green one, and then the green one is about 115. If you see on the graph, it's around 116. That's basically ballpark. And then the next one is going to be the all blue LED. And the blue LED is, let's see, about 73 millivolts. That's around 88 millivolts. So yes, it's in that range. So that is our experiment and data analysis.
So in regards to sustainability, our experiment highlights LED's potential as efficient receivers, particularly when paired with transmitting LEDs of similar wavelengths, suggesting applications in something like light-based communication systems, right? Also, LEDs offer environmental benefits, such as utilizing materials with lower carbon footprint, like aluminum gallium indium phosphide and indium gallium nitride, right? Furthermore, they outperform traditional light sources in longevity and energy efficiency as well, surpassing fluorescent lamps and tungsten filament light bulbs. Yeah. So in conclusion, we've confirmed a direct relationship between wavelength and emitted voltage. Our results verify the anticipated response of our receiver LED to the transmitter LED, demonstrating photoelectric effect as well. Despite obstacles, including circuit adjustments, changes in the operational amplifiers from the first procedure to the last procedure, and initial issues with the receiver LEDs, hindering light transmission, the project ultimately, achieved this objective, which we aimed at the start. Yep.
All right, open your. So this is our references that we use for our experiment. You can take a look at it if you're interested in it. And this is the end of our presentation. Thank you for your time and watching it.